Okay, so let's talk about problem one of the potential energy part two. So we have this mass that's at the top of an incline. It's released, which means it starts what? Starts at rest. It slides down to the bottom, across a horizontal surface, collides with a horizontal massless spring, compresses it to a maximum distance of 0.575 meters. We've got our spring constant. We've got the height of the incline. The horizontal surface is frictionless, and the slope of the incline is 27.7. Spring then pushes the mass back toward the incline. What vertical distance does it move back up the incline? All right, so this one is all about energy, conservation of energy, um, and how to think about this problem. So let's take a look at what we have. Now you'll notice the horizontal surface is frictionless. All right, so let's think about this. I'm going to draw real quick. We have an incline. On this incline is a box. We'll pretend it's actually flat on the box, on the line. All right, it comes down and slides across, and then down here there's a spring, and I'll just make that a different color of some sort. Do I have a spring texture? There's nothing that would be a spring texture, is there? We'll make it a gradient. Looks like that. Make it gray or something. Now I'm going to go back to gradient. All right. So this is our spring. I'm not going to try and draw a spring. We know a lot of things, but here's one thing to think about. Up here, what's the energy we start off with? Well, it's all potential, right? U sub I, U sub I. I'm typing. It's not doing anything. There we go. U sub I equals mgh. All right? All the energy at the top is potential. Then we come down here, and it hits this spring. All right? Once it hits the spring, what happens? All the energy here is again potential, but in this part of the collision, all right, what's potential energy for a spring? 1/2 kx squared. And we have all of that. We have k, we have x, the distance it's compressed. K is a spring constant. So we know how much energy we start off with here. We know how much energy we have when we get here. Question is, are those the same? Because the next part of the it, what happens, right? So let me get the box down here. Boom, 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 boom. Right? It presses against the spring, compresses it. Now we've got 1/2 kx squared energy down here. What happens next? Well, this sends it back, right? And at some point it comes to a stop on the slope. And at that point it has total energy, right? It's come to a stop. All of it's kinetic. I'll call this U final 2 is mgh2, right? mgh2. So we've got this initial height we go to, we slide down, we hit the spring, we compress. The spring uncompresses and sends it back up. So the question for you is how far back up the slope it makes it, right? And let me look at the question again real quick, right? Back up what vertical distance does it move back up the incline? So you don't have to worry about this distance. You only have to worry about this distance, the vertical distance. All right. So what you've got to find in all of this, what's conservation of energy mean? Right? We're going to start off the first bit, right? We have U sub I plus K sub I, K sub I. plus work due to non-conservative forces equals U final, right, plus K final. Well, we know U final, we know K final is 0 because it comes to a stop. We know K initial is 0 because it's sitting still. All right, we know everything here, so we can find how much work friction does in going along that distance on that part of the slope. Then we've got to figure out, okay, given how much work friction did per unit length, once you're down to this much energy that you have down here, how much work does it go do on the way back up? So this equation on the way back up, all right, and I'm gonna go ahead and put in zeros where we know that's 0, and we know that's 0, right? So here, what's our initial energy at this point? Well, our initial energy is F. Our kinetic energy is again 0 when we start out. This is the work done on the second trip, so I'm going to put a little 2 there. And this is the final 2 right here at the second height. All right. Oh, and we know, of course, that that again is 0. So we've got the trip down. That's the first equation up here. Then we've got to figure out, all right, what's the trip back up and what does it look like? And what we got to do is reason our way to, okay, so what does, oh, pardon me, what does that term right there, what should that term right there be? How does it relate to the total energy that we end up with? You know, because what's going to happen as it heads back up? It's going to have a certain amount of kinetic energy. That kinetic energy is slowly going to be drained off, both as it goes up the slope, right, and as it comes to a stop. That kinetic energy is fully represented by UF at this point, right? So when the block comes back and gets right here, 1/2 mv squared equals UF at that point. Your kinetic energy equals all the potential energy you had here. Then it heads up the slope, friction takes some out of it, and it comes to a stop. All right? So see how close you can come to figure out, how do we figure out what the energy that gets taken out as you slide up this? And a good way to think about it is, you know how much energy was taken out on the way down per unit length, and so you should be able to figure out how much energy is going to be taken out per unit length on the way back up. Right? Once you know that, you can solve for, okay, how far back up can we go? Right? All right, there you go for that one. Good luck, and let me know how it goes.